So here's a little test review as you're having your reading day and preparing for our Unit 2 test on Thursday. For this review, I would suggest that you're prepared to stop the video several times and work through the problem. So you're going to need paper, pencil, calculator, periodic table, a table of electronegativity to really absorb everything here and practice. All right, so let's get started. All right, so here are the topics that you're going to need to know for this test. So a great variety of topics and a lot of skills that hopefully you've already developed. I'm not going to read those to you. I'm pretty sure that you can do that yourself. All right, so what type of compound? Hopefully you were thinking that has to be an ionic compound with a positive cation and a negative anion. Don't forget those properties of those ionic compounds, like melting point. Which kind of compound has a low melting point? Now, anytime you're asked which type of compound, you should be thinking ionic or covalent. Those are your only two types of bonds or compounds. And if you were thinking covalent, you're exactly right. What strategy do you use when writing a formula for an ionic compound? So these are the ones with charges. So we're not using prefixes because they have those charges. Hopefully you were thinking the crisscross method, as you've seen many times. How about the overall charge of a compound? This can be either an ionic compound or a covalent compound. Hopefully you were thinking neutral or zero. What do we call an ion that has many atoms or multiple atoms? Hopefully you were thinking a polyatomic ion, things like sulfate, nitrate, sulfite, nitrite. And of course, those will be provided on the test. You cannot change those. Please remember, you can't change anything with the formula or the charge. And if you have to have multiple of those polyatomic ions in a chemical formula, make sure you put parentheses around it. What do the dots in a Lewis diagram represent? Hopefully you were thinking those are the valence electrons. Often those valence electrons, if you have a pair of them, they can be shown as a line for a covalent bond and two electrons. And if the electrons are not used in a covalent bond, what do we call them? Those are our lone pairs, exactly. All right, how about this compound right here? Again, use your periodic table. What would be the name and type of compound? Hopefully you're done and you've figured out that it's a covalent compound and it's arsenic pentaiodide. How about this one? Of course, it's an ionic compound. Cobalt-2 is with a 2+ charge, and so there is your formula. Hopefully you came up with that. Then molecular shapes and polarity. So what shape would this molecule be? Hopefully you're thinking this molecule, this boron trifluoride, is a trigonal planar. And here we go. How about silicon tetrafluoride? Hopefully you were thinking that's tetrahedral. And this one, this silicon dioxide, bent. If it exists like this, and there's other different ways that it can exist. And so keep in mind how you determine polarity. Once you're taking a look at the shape and the bonds, you've got to look at, when you're drawing those bonds, how are those atoms sharing their electrons? And that is with those electronegativity values. You have to subtract those. All right, so how about a molecule like this, NF3? Go ahead and take a few moments to draw that, figure out its shape, its polarity. Great time to pause the video. All right, so hopefully you came up with something like this. Of course, that is trigonal pyramidal. And then when you look at your electronegativity values, you can see that it is a difference of 0.94. So that means polar bonds. And the shape lends itself to having a separation of charge. So we have a polar molecule here. All right, so on to chemical equations. Again, remember the rules that these chemical equations follow. The reactants have to change chemically into products. If it's a physical change, we don't usually use a chemical reaction to show that. The products are different from the reactants with new chemical and physical properties, and they must be balanced so that they follow that fundamental law of the universe, that conservation of matter or mass. All right, so a question that you may see on the test is, what are the products and what state are they in? So take a moment, look at that. Hopefully you were thinking that the products are copper nitrate, copper 2 nitrate, which is aqueous or dissolved in water, and silver sulfate, which is a solid precipitate. And you'd be surprised how many people get something incorrect like that. Of course, what type of reaction? So again, look at your reactants on the left side, look at the products on the right side, and see what's going on there. If there's only one product, then you have synthesis or combination. If there's only one reactant, decomposition. Keep in mind that for a combustion reaction, your products are always going to be CO2 and H2O. So some of you have confused those with double replacement reactions. So really take a look at what those products are. All right, so here's an example of a combustion reaction. And so as you're presented with this reaction, what's the first thing you should always do? Yes, you should balance it. So go ahead and do that really quick. Great time to pause the video. All right, so here we go. So this is, again, the burning of the octane in your car. Again, those large numbers, what are they called? They are our coefficients. Now, if I told you how much energy was released here, you could also do stoichiometry on that. We'll get it more into energy in our next unit, but given a number here, like this is going to release 500 kilojoules of energy, you should be able to take a look that 2 moles of octane would release that amount of energy. All right, what about this reaction right here? Of course, what kind of reaction is it? Let's look at our reactants. I see an element and a compound. So obviously it's a single replacement reaction. So what would the products be? You will need to know that lead becomes lead-4. Of course, it has a charge of 0 right here. Any element has a charge of 0. Hopefully you were thinking, of course, this is a single replacement reaction, and hopefully you were thinking something like that. Now, of course, that reaction needs something. Yes, it does need to be balanced. So we would have to put a 2 there, a 2 there, and now I believe it's balanced. What do you think? All right, now to the stoichiometry part, calculating the quantities of chemicals. Again, what is the number of particles associated with 1 mole? That is Avogadro's number, 6.02 times 10 to the 23rd particles. All right, so again, equations, remember, are written in terms of moles, but you can't measure those moles in a lab. So how many moles of potassium are needed to produce 2.67 moles of hydrogen gas? And it's H2 because, again, hydrogen is diatomic. So great time to pause the video and see what you get. If you've got 2.67 moles of hydrogen, hopefully you looked at your balanced equation and you noticed that 2 moles of potassium produce 1 mole of hydrogen. And so 5.34 moles of potassium. Okay? How about the mass? If you have this number of molecules of hydrogen gas, what would be the mass? Hopefully you used Avogadro's number here in this conversion, and you came up with this number right here, 7.176 times 10 to the 10th. Now, of course, I'm going to need to cut that down because I see 3 significant figures in our problem. So I will need to make that 7.18. I don't remember if I did that for this video or not. I did not. And actually, that's not yet our mass. That is just our number of moles. But once we find moles, we can find anything. So if we have our number of moles of hydrogen gas, all I'm going to need is the molar mass. Multiply those together. So our mass would be 1.44 times 10 to the minus 9th grams. And I'm just going to check my math right there because that just doesn't quite seem right to me. And I'm not sure if I made a mistake there or not. 7.176 EE10 times 2. Yes, this should not be a negative 9. 3, 6, 9. This number here should be 1.44, but it should be times 10 to the 3, 6, 9, 10, 11 to the 11th power. I'm glad I noticed that because I hadn't picked up on that before. So again, rounded to 3 significant figures. So that should be times 10 to the 11th power. All right, here is another equation for you to do some stoichiometry on. All right, so again, think about the first thing that you have to do for this equation to do some stoichiometry. Hopefully you're thinking balance it. Yes, so great time to pause the video and do that. And so, of course, here we go. So that way we have 4 H's on each side, 4 F's on each side, and 2 O's on each side, and 1 silicon on each side. Now, how many grams of silicon tetrafluoride would you get if you react 5 grams of silicon dioxide with excess HF? So you have as much hydrogen monofluoride as you need. So go ahead, great time to pause the video and work through this problem. All right, so how did you do? Hopefully that you looked right here in the problem, starting with these 5 grams of silicon dioxide and started right there. And of course, in order to do anything with an equation, you're going to have to convert those grams of silicon dioxide to moles. And so hopefully you looked up the molar mass of silicon dioxide. I got 60 for that. And then we can look at our equation and notice that 1 mole of silicon tetrafluoride equals 1 mole of silicon dioxide. Our molar mass of silicon tetrafluoride is 104 grams. So we come up with 8.65 grams of silicon tetrafluoride, excuse me. And of course, what do we call that number right here? Hopefully you're thinking that is our theoretical yield, and you are exactly right. Notice that this silicon tetrafluoride is forming a solid right here. So we may have a precipitate right there in this double replacement reaction. So always be looking for those. Now, in the lab, you only produce 5.92. So remember this number. 8.65. Hopefully you've gotten that written down. That is your theoretical yield. So if you're working in the lab and you only produce 5.92 grams, what is your percent yield? Another great time to pause the video. All right, how did you do? Hold on, I've got a mistake here. Because that should be 8.65 grams. I must have clipped the wrong thing from my paper. So this should be 8.65 grams. And that's what I was doing, clipping them from paper. So your percent yield is not going to be as high as what I originally had. 5.92 divided by 8.65 times 100. Oh, so we didn't really get a very good percent yield here. We only got 68.4% yield. Now, obviously, if you can do all of that, and you saw me make 2 mistakes as I was going through there, I'd already prepared this PowerPoint, which I don't think is too bad. And so that would be my goal for you for the test. I'm sure your goal is to miss no problems on our test on Thursday. But I hope this helps you as you're reviewing. Please reach out if you have any questions.